A few years ago, while I was out for a walk, I was thinking about the asteroid strike that led to the eventual extinction of the dinosaurs some 65 million years ago, and in particular I was wondering how much energy was released. And so after a few more minutes of walking, I came up with an estimate. It's not uncommon to be asked these type of questions at technical interviews, as it allows the candidate to be assessed on a number of important attributes necessary to help solve real technical problems. These include being aware of the world around us, being able to make judgments where data are uncertain or unknown, and lastly, having the mental dexterity to deal with pressure situations. The hard bit of the question is not in the computation, but in how to make reasoned, plausible estimates for the input parameters, given that no other information is provided. In this video, we will discuss the type of approach that is suitable to answer such a question. So let's move on to the estimate. As the asteroid would be travelling at high speed, the only thing to consider is its initial kinetic energy just before it entered the Earth's atmosphere. All of this energy would be transferred to the Earth, partly in the atmosphere, but mostly on impact. As any secondary school student should know, the kinetic energy is given by the equation half mv squared, where m is the mass in kilograms and v is the velocity in meters per second. This is essentially the only equation you need to use in this problem. We can estimate the velocity directly, but we can't directly estimate the mass of a large object with any reasonable accuracy. However, mass is equal to volume times density, and volume is dependent on the size of an object. Therefore, we can estimate the mass indirectly by estimating the size of an object and its density. We know that the asteroid will have an irregular shape, but to work out the volume easily we need to assume a simple shape, such as a cuboid for example, for which the volume is simply the length cubed. I originally assumed a spherical shape, and the simplified equation for the volume of a sphere is shown in the box for those of you who are interested. A sphere of the same dimensions as a cuboid has half the volume, but differences such as these due to shape are insignificant because the largest error in the estimation of mass will be due to the error in the estimate of the object's size. This is because the mass is proportional to the cube of the size term. For example, if the size was wrong by a factor of 10, then both the mass and the kinetic energy would be in error by a factor of 1,000. It should be noted that in contrast, mass is not very sensitive to density, as it's only directly proportional to this parameter. However, the kinetic energy is sensitive to the velocity, as it depends on a square term. We can now proceed to estimate the size, density and velocity. We will look at the size first, as it's the hardest to do. Now, unless you have a scientific background or a good awareness of space science, then it may be difficult to estimate the size and velocity of the asteroid. Young students in particular find it difficult to estimate real-world parameters due to their inexperience. When posed this question, a typical response is, "I don't know," or "I haven't got a clue," because they don't know where to start. In this situation, one approach is to try and derive a range of values, as we generally have a better feel of what the plausible maximum and minimum value is of something. So let's try this for the size estimate. Now the Earth is around 8,000 miles in diameter, and the Moon is about a quarter of that size at about 2,200 miles. I think it would be fairly obvious to most that the asteroid was very unlikely to have been as large as the Moon, as such an impact would have had far greater consequences for the survivability of Earth. So let's look at something smaller, say an object that is about 7 times smaller than the Moon, at 300 miles or 500 kilometers across. This appears to be a better plausible upper limit for the size of the asteroid, so we will stick with this. Now, how small might the asteroid have been? Well, it must have been bigger than a football, say. How about a building, such as a 10-meter house? Probably too small. How about a 50-meter school? Now that seems more plausible, so we will go with that. Thus, we have now derived a range of 50 meters to 500 kilometers, or 5 times 10 to the 1 to 5 times 10 to the 5 meters, a span of 4 orders of magnitude. We could now just use the simple arithmetic mean of these two numbers, and we would get a figure of around 250 kilometers. However, there's a problem with this. Because we have only averaged two numbers with a huge range, the mean is skewed very disproportionately towards the larger number. Although the mean falls midway between the two numbers in a linear manner, in terms of proportion it does not. Relative to the mean, the larger number is twice as large, whilst the smaller number is some 5,000 times as small. Thus, the minimum size is having virtually no influence on the value of the mean. What we would like is for both the minimum and maximum estimates to have a similar influence on the mean value. We can achieve this by taking the geometric mean, which averages proportions. Geometric means are normally derived by essentially averaging the logarithms of the numbers. Fortunately, we have chosen two numbers where it's possible to find a geometric mean mentally without requiring logarithms and a calculator. Now, the maximum estimate is 10 to the 4, or 10,000 times greater than the minimum. The geometric mean should fall in the middle. In other words, relative to the mean, the larger number should be 10 to the 2, or 100 times greater, while the smaller number should be 100 times smaller. 100 times the minimum value of 50 meters gives us a mean of 5 times 10 to the 3 meters, or 5 kilometers. This is much better, as now, relative to the mean, the maximum value is 100 times as large, whilst the minimum value is 100 times as small, and so both have the same importance. When I originally did the calculation, my size range was between 1 kilometre and 100 kilometres, based on my prior knowledge, so I took the geometric mean of 10 kilometres, which is of the same order as the 5 kilometres we have just derived. You can see how a simple approach based on first principles can lead to an estimate that is plausible. We will use 10 kilometres in the subsequent calculations, as it's a nice round number. That's the harder bit out of the way, so let's move on to estimating the velocity of the asteroid. We will try a simpler approach here. In the absence of prior knowledge, we could, as a baseline, use the speed of familiar flying objects such as an airliner or a rocket. An airliner generally cruises at around 500 miles an hour. However, when viewed from the ground, an airliner appears to be travelling relatively slowly. From fiction movies or footage of real meteoroid strikes, space objects appear to move much quicker in the sky than an airliner. Thus, the asteroid velocity is likely to be many multiples of this baseline 500 miles per hour. Maybe 10 times or 20 times could be a plausible estimate. When I did my estimate, I assumed it would be the order of the Earth's escape velocity of 25,000 miles per hour. This is the velocity required to fully escape the Earth's gravitational field, and is required to be achieved by rockets such as the Saturn V that took men to the moon. I used escape velocity as a reference because the asteroid would have had to escape the gravitational field of another large body in order to arrive at Earth. We have derived the velocity in miles per hour, as this unit is familiar in the UK and America. However, we need the velocity in meters per second. This is where it's important for the young student to learn and retain important facts and figures, including conversions, particularly if you intend to work in a technical job. Now, knowing that 10 meters per second is approximately equal to 22 miles an hour, I just assumed a velocity of 22,000 miles an hour, which led to a nice round value of 10,000 meters per second, or 10 kilometers per second. So we shall use this value. Let's now move on to estimating the density of the asteroid. An asteroid is a rock, and we know that rocks are denser than water. Every school student should know that the density of water is taken as 1 kilogram per litre, or 1,000 kilograms per metre cubed. But how much denser are rocks? Most people will know that they are less dense than common metals like steel and copper, but unless you know the relative density of steel or copper, that doesn't help. So I'm afraid in this case you would have to take a guess, but that's not so bad, because as we discussed earlier, the asteroid mass is only proportional to the density. And so if you're out by a factor of 5, or even 10, it's not the end of the world, if you pardon the pun. From prior knowledge, I knew that rock densities are typically 2 to 3 times that of water. So I took 2 times, or 2,000 kilograms per metre cubed, as it's a nice round, simple number to use in the computation. At last, we're in the position to calculate the initial kinetic energy of the asteroid, and we can go back to an earlier slide. We know that mass is equal to the size cubed times density, and using the estimates that we have just derived for the size and density, we can plug in the numbers and arrive at a mass of 2 times 10 to the 15 kilograms. Finally, we can use this mass in the equation half mv squared, together with the velocity estimate we have just derived, and we end up with a figure of 10 to the 23 joules. It should be noted that the mental maths can only really be done using numbers in standard form, and you clearly need to be familiar with the manipulation of powers or indices. I have another video explaining the laws of these. Now we can compare our estimate of energy with the published figures for the impact energy. The ones that I have come across range between 1 times 10 to the 24 to 6 times 10 to the 25 joules. This range is based on assumed asteroid sizes of 10 to 80 kilometers, velocities of 20 to 30 kilometers per second, and a relative density of around 2.7. In this simple example, we have only estimated the initial kinetic energy on entering the atmosphere, whereas the published figures have estimated the impact energy after some energy has been dissipated in the atmosphere. Nevertheless, our simple estimate is broadly comparable with the more detailed calculations. Now you may be wondering what such a large value for energy actually represents, as it's difficult to get a feel for it. So let us quickly compare the energy to something we can better relate to. First, let's use the central estimates from the published data of 5 times 10 to the 24 joules. What is this equivalent to? Well, as the impact energy was released in an extremely short space of time, we can only really compare it to a set of nuclear bombs all going off at once. In fact, this amount of energy is equivalent to the yield of around 100 billion Hiroshima-type fission bombs, and around 1 million times the yield of the world's current nuclear arsenal, mainly thermonuclear bombs. This is still an unimaginable amount of energy. I've included 2 further less violent comparisons. 5 times 10 to the 24 joules of energy is equivalent to around 10,000 years worth of the world's primary energy consumption, and around 1 year's worth of the solar radiation that falls onto the Earth. Amazing, isn't it? I hope you enjoyed this video, and thanks for watching. See you in the next one.